Well, good morning. Welcome to session 1 on unsteady analysis, new requirements for CFD post-processing. My name is Darrell Rittenberg, and today I'm joined by Scott Emley.
Hello, everyone.
Good morning. Today we're going to spend about 25 minutes talking about some of the challenges with evaluating unsteady CFD results. And this is actually the first of 3 topics. We'll start with more of a theoretical tinge, and then we'll actually move towards a more tutorial-based session for strategies for unsteady simulation reporting, and that will be in the next few weeks. Finally, we'll actually have an overview for TechPlot 360 users on the new release TechPlot 360 2011 R1, where we'll have a tutorial on unsteady post-processing. So this is really the first of 3. So welcome. I wanted to start by getting a sense of how the audience is using unsteady analysis. And so I was going to open with a polling question. And so I'm going to try to do this quickly. I know that we don't have a lot of time, so I'm going to go ahead and launch the poll. And you should see the poll up on your screen. And you can vote now. What percentage of your work uses unsteady simulation methods? And it could be anything from CFD, but you may do structural analysis, you may do fluid structure interaction. And I'm going to keep this open for just until we have about 75% of folks who have submitted an answer. So we're up to about 60%, so if you haven't chimed in, please do so. And it looks like we have about 75, so let me go ahead and close the poll. Sorry if you didn't get a chance. And I'll go ahead and share those results so you should be able to see those now. So it looks like about 20% of you are doing, about 70% of the work that you're doing is unsteady. We have some 6% aren't doing any, but then you can see that the 30 to 50% range seems to be probably our highest bucket of people, and that's kind of consistent with what we're hearing.
Yeah, I think so. I mean, nearly everyone is moving in that direction. Flow is inherently unsteady, and as you go to higher resolutions and you're looking for more physics, you'll need to do more unsteady.
And that seems to be something that in my travels that I'm seeing more and more people, and it makes a lot of sense. I wanted to put this in context for a moment. So today we're going to talk about why people are moving to unsteady simulations. In addition, we're going to spend some time talking about the challenges with moving from 3-dimensional to 4th-dimensional data, or in fact, it could be multidimensional depending on what you're looking at. We'll talk about some of the analysis changes, things that you need to do in the flow field that are different. We'll talk about qualitative and quantitative requirements, and then we'll actually look at an example of vortex shedding and use that as an opportunity to highlight some of those changes. And we want to make sure there's plenty of time for questions. So if you've got some questions that you wanted to make sure that we touched on, please have those queued up. And as we get towards the end of this discussion, we'll have ample opportunity to talk to those questions. So I wanted to put this in context for a moment. And I think we all live in an engineering or scientific world, and we often forget about other industries that are running into very similar challenges. And I think this is an area, for example, in the medical industry, and we talk about people who do CT scans. And it seems like a pretty innocuous type of scan. It's very popular, but it really illustrates not only where people are going with data, but really some of the challenges. Specifically, if you go back just 2-3 years ago, an average CT scan was about 100 scans of 512 squared, about 50 megabytes of data. Mm-hmm. Now, if we look today, an average scan's about 10,000, same resolution, and about 5 gigabytes of data. Again, data's getting larger, but what's interesting about this is that right now some of the researchers, and actually where this is going, is medical imaging's going unsteady too. In fact, now there's a fair amount of research around looking at some of these time resolved data, And specifically, we're finding that people are looking at about a terabyte of data, which is a lot to look for one simulation. So out of curiosity, before we go forward, if you could let me know just by submitting a question or a chat if you're having audio problems, serious audio problems. All right, we're going to switch over to telephone. This is going to take about 20 seconds here, so please hold on. Okay, sorry, that took just a second, so hopefully the audio is a little better now. Okay, so again, if we just take a look at this data, and now if we kind of extend that to numerical simulation, and we talk about folks in numerical simulation, still just a few years.
No, CFD simulation. And more bleeding edge stuff is well over 1 billion cells now.
So that's, again, not to suspect that we'll see a shift to 500 million cells, pretty commonplace, probably within the next 12 to 14 months.
Yeah, the drivers for this are really the available computer power, and the computer power has increased dramatically. Actually, the size of the file has also.
Now, that doesn't, that implies the steady state phenomenon. Here's people, that should probably go back about 5 years, 50,000 cells. Today, the average person that we're talking to is looking at probably 10 million cells and 100 time steps. Now you're getting up into 50 gigabytes a day. And that becomes more of an issue, because not only accessing that data from a hard drive, as both Scott and I have learned, that one of the larger the data, oftentimes the reading it from the disk becomes a rate-limiting step.
Yep. It's the hardware. You know, it's the one thing that's not totally electronic. It's actually got a spinning device.
So what we're expecting is in the next 12 months, people will be looking at nominally 100 million cells and perhaps up to 1,000 time steps, if not more. Now we're getting into the terabytes of data.
Yeah, terabytes. I mean, what we're seeing in aerospace, but if you may actually be seeing something significantly. A petabyte of data, 1,000 gigabytes or terabytes, 1,000 terabytes.
A lot of data.
A lot of data.
Okay, we're going to. Can't exactly say why. Okay, we had one person say we're already doing 100 million cells and 1,000 times. So I guess we're behind the times. So in that context, we just want to get a sense of, for the audience, how large are your simulations? And so we're going to look at the next quick check-in here. So the poll is open. If you could quickly vote, on average, how big are your data? And it looks like we're getting some folks. We've got 1 or 2 people who are in the 300 million cell models, but it looks like 75 to 150. We have about 57% of the folks who have voted. We're waiting until we get to about 75, and we'll go ahead and show you the result. So if you haven't voted, now's your opportunity. And we're going to go ahead and close the poll, and I'll show you kind of where we ended up. Okay, so very quickly, if we take a look then at the results, and they should pop up here in a second. Okay, so you can see that it really depends people have been exploring these methodologies. One, of course, being this biomimetic simulation, like looking at the flight of a bumblebee or a dragonfly from our most recent story. But there's a fair amount of interest in rotorcraft.
I love this simulation, by the way. It's so complex fluid dynamically. You see the vortices interacting. It's quite cool. But on the moving body simulations, obviously a very common one is rotorcraft, helicopters, and at times the performance of these vehicles. And there's obviously a lot of things going on fluid dynamically there on this fruit fly to our right. Other areas are turbulence. Turbulence is inherently unsteady. Now we model turbulence with equations that model the unsteadiness in our Reynolds average Navier-Stokes equations, but a lot of people are going to an actual simulation of the unsteadiness through large eddy simulations, detached eddy simulations, or even direct numerical simulations of the turbulence. Acoustics, inherently unsteady. There are methods that can model simple acoustics in a semi-steady form. And a frequency domain, for instance, but multi physics modeling, the aeroelasticity. No audio. No audio. Okay. We're still, I guess, having some audio problems. I guess we'll. Okay.
Welcome to GoToWebinar, Web Events Made Easy.
Again, I apologize for the audio problems. I'm not sure where they're coming from. So we'll continue to go here, and again, we'll see whether or not the audio problems will fix themselves. Again, if you're having difficulties with audio. Okay. So quickly, let's go ahead then and continue. We'll go ahead and look at welcome to the fourth dimension here. And one of the things that we're very interested in is, the steady-state methods in CFD are pretty well established. I mean, we've been looking at steady-state results for 30 years. But when you make that transition to the fourth dimension, you really are posed with an entirely different set of problems.
Yeah, this reminds me of back in the late 80s and early 90s when we were doing mostly two-dimensional CFD. And you'd go to the conference and somebody would be talking about a new algorithm for fluid dynamic CFD. And they would present their two-dimensional results and say the extension to 3 dimensions is trivial. And in some ways it's a similar problem here. We're actually going up a dimension. And on the screen, well, the screen is two-dimensional, but we are pretty good at projecting 3-dimensional data onto the screen in a meaningful way. But 4-dimensional data, you can't project the 4 dimensions onto the screen. It's just not something that we can comprehend in totality.
So you have to come up with new methods.
And that's really, if you think about it, we talk about this unsteady post-processing for the most part, where people have kind of settled as, hey, I'll just make an animation, which is, I think, a good start point if you're looking at qualitative information. But the real meat, the real qualitative and quantitative information requires a different level of analysis.
That's right. You know, for the qualitative, typically we use animations. It's something that we deal with on a daily basis, watching TV or whatever. We understand watching things vary through time. But quantitatively, you have to start looking at other things, dimensionality reduction through integrations or time-dependent scalars, looking at specific values in the domain, Fourier transforms, looking in the frequency domain. It's still, you have still lower dimensionality, but you can use that to help you understand how things are varying through time in a more meaningful way, perhaps. And then just statistics, you know, looking at min-max, average, and standard deviations of how things are varying over time.
Okay, so what I'd like to do is let's talk a little bit more detail about streak lines, streamlines, and particle paths.
Yeah, that was the final one. Is looking at your vector field. It's tricky to begin with, but when you're talking about time-dependent data, there are really three different ways of looking at it using these tangent curves. The one that we're most familiar with are streamlines, and streamlines are well, they're all tangent curves, first of all. So they all represent some sort of an integration through time of a curve that is everywhere tangent to a vector field. For streamlines, the vector field you're looking at is the velocity at a given time, and the whole integration occurs at that time. So you're integrating over a pseudo time for the tangent to the velocity field at that time. Now that may or may not be meaningful to you. For particle paths, I think have a more significant physical meaning, and that is everyone understands you know, releasing a balloon in the atmosphere and watching it move around, and that's basically what you're doing with these integrations. So the difference between that and the streamline is that you're integrating the actual velocity that is varying through time, and so this gives you a line which represents a space-time curve. So it's actually going through all 4 dimensions, and generally you either project that to 3 dimensions, so you just see this line that is constant over time, or you actually look at the motion of the particle through time in some sort of an animation. Finally, you have streak lines, and streak lines are what is represented physically by a smoke line that emanates from a point source, like a smokestack. And you can imagine just releasing particles, smoke particles, rapidly. It creates a line, and then that also has a very solid physical meaning.
Okay, so if we then look at an example, perhaps, of streak line, particle paths, and streamlines, and we can actually look at this example as an animation where you can see that the blue line represents the streak line, and you can see that the green line is the actual particle path, whereas the black line here represents the streamline, which is probably where most people will actually use more streamline analysis, where it may not be appropriate in a time-resolved solution.
Yeah, this is a very simplified flow, so this represents just a constant flow velocity and angle oscillating up and down plus or minus 30 degrees. That's why you see that the streamline is actually straight, because at every time it's constant velocity angle, and so it's going to be straight. The particle path, of course, sees the velocity starting out level and going up and then going down, so it represents some sort of a sinusoidal motion. And then the streak line is repeated particle releases. So the first particle on that is actually follows the particle path, follows the green line, and you can see as it goes. The streamline in this case may not be very meaningful to you because it just is going up and down. And you'll see this in some of our other other animations as well, where the streamline really jumps around a lot. But the streakline and particle path, either one gives you a good idea of what's actually going on in the flow field.
Now, if we extend this to the analysis world, we've talked about streak lines, streamlines. We really start to think about when we do quantitative analysis of time-resolved solutions, really we need to look at the integrations in a little more detail in terms of mass flow rate, forces and moments, and we'll talk about that in the subsequent slides.
Yeah, I mean, the mass flow rate is especially in internal flows. You're going to be looking at how that varies through time. Forces and moments, of course, are critical in aerodynamics. Mass-weighted averaging is something you do a lot in turbo machinery, where you're actually looking at mixed out quantities, and just averaging over time is you know, of course, is just another way of looking at your results. Now, in turbulence, often you do Reynolds averaging, so you would do this especially with the direct numerical simulations to get a feel for how your quantities that you would use in a turbulence model might compare to what you're getting out of your numerical simulation. And then finally, frequency domain is critical in acoustics and aeroacoustics.
It looks like we're still having some audio problems, and I apologize for that. We're going to try one more phone to see whether or not that helps. So I'm going to put this on mute for just 1 second while I switch to a telephone. Hold on 1 second.
Welcome to GoToWebinar, Web Events Made Easy.
Okay, this is come on. Okay, hopefully this is a little better. We'll try, this is the last, we're actually going to switch over to the iPhone. We'll see if AT&T can do a better job.
Can you hear us now?
I am curious, real quick, if you could just let us know. Well, I'm not sure much better. Hey, there you go. Okay, well, there you go. So if you're going to be putting on an event, just turn to your cell phone. You'll be better off. So let's go ahead then and talk about some of the other reasons why people look at these multi-phase flow. It's about the same for some people. Okay. Some of the things that you look at when you start talking about, say, multi-phase reacting flow, really you need that quantitative information. You need everything from catalyst dispersion to
It's to a good overview, but most of the time that's not enough. You need to know what you have answers that you need. You have questions you need answers to, and to do that, you really need to get down to XY plots and some of these integrations. You know, we have some examples of how we use, what you might need things like mass flow rate for, and how it might affect or how it might come out. So, you know, an obvious example is up here in the left, where you have this rocket nozzle, and there you might be looking at rocket ignition and or, you know, changes in the thrust, and you need to you know, your waves propagate through the nozzle and moves up, and so mass flow rate is a common way to do that. Obviously, if you're pumping things, you want to look at the flow rates and variations in the flow rate, and this is especially important in internal flows.
And we're seeing more and more people also looking at two-phase flow transient, where they may be looking at oil cooling or fuel pumps. So this is becoming an area where, again, it's very intuitive to look at both the animation, but there are some significant mass flow rate implications that need to be resolved in the simulation, and so we're seeing that to be more and more of a trend. In addition, of course, to the forces and moment calculations, we talk about the distribution of loads as a function of time. I guess the example of rotorcraft here, but there's also other examples.
Oh yeah, I mean, this happens in maneuvering of all aircraft, and you need to be able to do your integrations through time, and then you can actually look at how that varies. And especially in aeroelasticity, where you're looking at the actual interaction between the structural mechanics and the fluid mechanics. Knowing your forces as a function of time is crucial to that. And
we actually found an example. I might have to move it over. So hold on. I'll see if you can see that. Okay. So what we're actually looking at is, again, we're with vortex shedding of a cable, and you can see that you get the oscillation. And we have a great example locally of vortex shedding problems developing, Gertie.
Oh yeah, yeah. Imagine they have a spherical grid. This is the sort of thing that happens also in the cables that hold down various things like the oil rigs and offshore oil rigs, and you get these vortices shedding off of it, which actually force the motion of the cable, and then that in turn actually enhances the vortex shedding. And in certain situations, that can get totally out of hand, like in galloping Gertie, and cause structural failure.
And so that's certainly an area where looking at an unsteady simulation can be perhaps more informative and certainly more interesting. I don't know if anyone's ever simulated these combo bridge disasters, but it's been fun to do so. Of course, once you move into time dependent, you start to really have to analyze both the frequency domain and time domain. Of course, quite important.
It's obvious. We listen in the frequency domain. That's how we hear, and so it's natural to go to look at the frequency, the amplitude of various frequencies that make up your sound waves. The same thing occurs in aeroelasticity, where you're actually flutter occurs when you get these natural vortex shedding frequencies that match up to certain dominant structural modes, and so just to get an idea, even if you're not doing the coupled analysis, just to get an idea if you're going to be having flutter issues, it's nice to actually switch over to the frequency mode and see where your dominant frequencies are.
Okay, so what we'd like to know from you is, what are your current challenges in regards to your analysis of unsteady results? And so we've kind of heard from a number of people what are the key things that they've run into. Is it creating animations? Is it the analysis of the derived quantities? An issue that we're running into, of course, is loading these extraordinarily large simulation data. Or is it a little of everything? So we'll go ahead and leave this open again until we have about 75%. Looks like we have some all of the above. Seems to be taking the lead. All of the above. All right. We're at about 60%, so we'll give it another 30 seconds before we move on here. And as soon as I'm done, I'll go ahead and post these to you. Almost there. Looks like, okay. So I'm going to go ahead and close the poll and I'll post this back, and then we're going to actually walk through a couple examples in TechPlot. Some people had asked. Okay. Or going to time to post-process was an issue that wasn't in there, so we'll definitely add that. It's a good one. Okay, let me share those results with you very quickly before we move on. Okay, so you can see that nominally half the audience basically said all of the above. So we'll try to address all of the above. Okay, let me hide this. We're going to go ahead and continue on. I again apologize for the audio problems. Hopefully it's a little better now. Let's go ahead and we're going to actually take a look at this example where I'm going to go ahead and with the animation. One of the challenges we see when we're using a PowerPoint across GoToMeeting or GoToWebinar is that it looks like it doesn't do a good job of updating very quickly. So I've actually gone ahead and posted these up to YouTube. So if you're at all interested in seeing this animation and getting a higher resolution animation, you can go ahead and get those on directly off of YouTube. And so we'll send a link along to all the folks here. Again, still the audio is going in and out. I just don't know what's going on. Okay, so let's go ahead then, and in this case what we're looking at is vortex shedding around the cylinder. You can see the cylinder is fixed in this case. And we're looking at those vortices. So we're looking at, in essence, vortex shedding here, and you can see that phenomena as a function of time. So I've actually done this as a pretty highly resolved simulation, and we're looking at about 1,000 time steps. When I made this animation, this is probably where most people would have stopped, and I just did this on my laptop. It could take a couple hours to do. Yeah. Let's go ahead then and take a look at an example. So let's see if we can go ahead and get out of this, and we'll just pop into TechPlot. So this is an example. So that's the same one I'm looking at, waiting for the next screen. And I know that the update rate looks like it's not totally perfect, but one of the things that they say we can do is if we make the image just a little bit smaller, it might update a little faster. Okay. So if we go ahead, let's just take a look at this. We'll look at what most people would start with is just to animate the data. So it looks like you're getting about one every every 4 or 5 frames maybe.
Yeah, and you seem to be getting some strange lines showing up on this.
I don't think
they're not getting that? Okay.
No,
it's just us.
Just us. Yeah, so that's kind of the first step. Of course, this is probably something we're looking at a simple slice, and if I look at that slice, let's be perpendicular for a moment, and we'll zoom in a tad, and we can do that same animation now. And again, you're just looking at vorticity here. So you can start to get a sense of how the flow is developing as a function of time, which is a good thing to start with. But we wanted to go back to, oh, they are coming across well. Okay, well, I apologize. I guess it is coming across well. That's good to know.
Yeah, good.
Good. All right. So again, you can go through the animation, and for the most part, if you look online or you go to a presentation, this is about the extent that people would show. But we wanted to show you some of the things we talked about earlier in terms of looking at stream traces, streamlines, and streak lines. So perhaps let's go ahead and start with looking at streamlines. So if we're going to do 2 things, and first thing I'm just going to deactivate this guy. And I'm actually using, just for context here, the version of TechPlot that I'm using here today is actually a beta that has been posted, but these include some functionality that are not available in the current version of TechPlot. So some of the things you're seeing, you'll have access to soon, but you don't have, if you want access to earlier, we certainly would encourage you to participate in a beta program. Okay, so let's go ahead and go to the beginning of the simulation here, and we're going to drop in some streamlines. Now again, as Scott pointed out, these streamlines are just the instantaneous integration through the flow field.
And you can actually see that the streamlines are cutting in and out of that plane of that slice plane. You can see that, yeah, it's on the other side. So there's a significant amount of 3-dimensionality to this flow field, even though it's really flow parallel to a cylinder vortex shedding. You're getting some turbulence effects going on.
So if I go through again now and animate, you can see those instantaneous streamlines And you can see that they kind of wiggle and go around, and you can see there's loose circulation.
Yeah, they're jumping in, especially if right behind the cylinder. You can see a lot of jumping around of the streamlines. And that's our artifact of the fact that it's actually integrating a separate streamline at each time. And so you're going to see a lot of motion.
Now, to just illustrate, in effect, the dimensionality here, we can quickly look at the multidimensional. We'll look at each of the independent axes here. So you're looking at, here's a projection in the XY plane, here's a projection in the YZ plane, and this is the XZ plane here. And if we go ahead now and we'll do that same animation, we're going to just animate one more time. So you can see now that you can actually see that dimensionality a little more just by looking at the different projections, principal projections. Okay, so we want to actually then take a look at perhaps two things. So one of the things that comes up a lot is if you wanted to look at, say, the simulation and you wanted to look at the streak lines and particle paths, how does one do that? So we're going to take a look at an example here. So I'm going to pause this and let's just pop into to another one here. So this is that same cylinder, and you can see those are the stream traces. And what I've done is I've added in some streak lines. So we're going to go ahead and animate those now.
Yeah, the particles actually represent those particles released. As I mentioned before, frequent release of particles, and they're connected by a line. Those are the streak lines, and so you're actually getting a view of both particle paths and streak lines here.
So if we then switch over, we talked about, remember the green line that we showed in a moment. If we delete all of these, we can go ahead now and show, say, the particle paths. And we can calculate those as well. If we show them, you can see that the particle paths don't animate because this is actually the path over time.
This is the path through space-time projected back into the 3 dimensions of space. So they're not going to change. That's actually the path that the particle takes as it goes through time.
So you can see then, you can get a lot more information then by looking at, say, the stream traces, or I'm sorry, the streak line. Those are just looking at simple stream traces. So let's go ahead and delete all these. They're not overly important. We'll go back to showing an isosurface here. And perhaps we'll look at a different isosurface very quickly. How about just vorticity magnitude and surface locality. So there's the vortices that we can quickly show here. And again, we can do that kind of animation. Now, one of the things that people have often asked about is, well, you know, when I put together a PowerPoint presentation, they want to be able to look at, say, deltas between time steps, or even to take a look at multiple time steps. And perhaps it would be easier to see that using a simple slice, where we'll just look at, well, okay. So if you can imagine, oftentimes you want to show, say, a different time step. And one of the things that we've done and will be available in our next version of TechPlot is how to make this as easy as possible. So I'm just going to go ahead and copy this frame, and I'll paste a couple in here. Let's see how many I want to do. 5, 6, 7. And if I just tile those very quickly, let's make an array here. So now I have an array of each one of these plots, and you can see that they're all identical. And I can go through now and look at each one and do a delta of time step. Now, we're working on making this a little more automated, but I think it's worth just exploring how you can take a look at each one of these. So you can have multiple time steps on here, and in effect, if we wanted to look at, well, what is the time there, you can just quickly use time equals, and then it's the solution time. So in effect, we'll just add in solution time here. Okay. So then once we have the solution time on screen here, so there's a couple of things. You know, again, if you're doing your analysis, you may want to look at multiple scalars, see that the times may or may not be the same. If we wanted all the times to be the same and look at different scalars, again, we built in the capability
to link solution time across frames, so that's why. And then what that does is if I hit animate now, you can see that all the frames will animate simultaneously. So it gives you, okay, how big are these files and how are they loaded and how long does it take? Very good question. This is about 2.5 gigs of data. It's about 80 million cells total. Each time step must be close to 1 million cells. So it's not very big. Good question. Okay, so you can see, I'll go ahead and pause this. So then I can really interrogate time. Well, if I want to get in and do a little more quantitative analysis, I also have the opportunity to analyze on a point how things are changing as a function of time. So I'm going to create a quick view of the data here. Now I can actually click anywhere in the domain and create a new, say, store through time. Again, it gives me an opportunity to quantify the results on screen.
Yeah, this is critical, and this is a new capability. But you know, just looking at how things vary in a given time is only part of the picture. You need to be looking, breaking in the fourth dimension, and actually doing your analysis through the time dimension as well. And so this is going to help people a lot with their unsteady simulation.
Well, a couple other things, and then we'll kind of open it up to questions, and we'll keep open on over here. We have added a couple who are looking at simulations on the plot3 front, which is where these data come from. We now have the ability to load grid and multiple solution files. So that was one thing that we added. On the CGNS front, we had a fair amount of interest in looking at CGNS files. So we've actually updated. We've had the ability now to load multiple CGNS files as well. So we've done a fair amount to kind of address how these data are being loaded. Okay. What are the computer hardware requirements? Okay. Well, let's actually. Why don't we go ahead then and let's just quickly summarize, and then we'll turn it over to questions. It looks like we have quite a few questions here, so let's quickly summarize, and then we'll get to answering some of these questions. Again, if you've got some questions, we have quite a few here, but if you would go ahead and start typing those in, and we'll go ahead and address them. So let me.
While he's doing that, I'll answer a couple of them. Do you support overflow adaptive grids? Yes, we do. Vorticity and non-uniform grid and across block interfaces, yes.
In terms of computer requirements, the computer that I've done all the work on for this is an Intel quad core. I've got about 8 gigs of RAM running Windows 7. It's a laptop actually, and for me, I think I was able to load 2,000 time steps, so that's probably not too big. There's the new CGNS data loader read and support HDF5 format.
Not at this point. That's actually interesting. We can do that, and we're doing it now, but we haven't yet done that.
Just quickly to summarize, so we've talked about why people are moving to unsteady results. We've talked about some of the challenges with the fourth dimension. One of the things that we want to spend time on in the subsequent sessions would be strategies for both animation, integration, and FFTs. So that'll be something we'll be talking about in our next session. The other thing that we're just hinting at, but the fact is data is going to grow. It's going to be, as someone already pointed out, we're looking at 100 million cells and 1,000 time steps today. That's some change. People are going to be looking at 500 million unsteady. So we're looking at different strategies on how we can keep pace with data size, perhaps in a novel way.
Right. Don't want to go into too much depth there, but in the end, it comes down to getting the data off the disk and then effectively utilizing the memory you have. So going forward there.
And that's just a precursor, so we do have two more topics coming up. One will be a little more tactical around strategies for unsteady simulation reporting, and that's going to be mostly around quantitative analysis and some animation creation. In the last, we'll talk about the release of TechPlot 360 2011, which we're targeting for towards the end of the first quarter, beginning of the second. And let's go ahead and start to get to the questions.
There was a question about the accuracy of the calculation scheme on vorticity. It's slightly different with ordered and unstructured grids. With ordered grids, it is second order accurate center and time differencing for the velocities. And with unstructured, it is uses a moving least squared scheme. Actually, I think it works out to third order in space. And somebody said they saw some discontinuities. Discontinuities can occur if you're dealing with adaptive grids where the lines don't match up. You get some slight discontinuities because there's an added line there, depending on how it's handled in the actual grid.
There was a good question on parallel processing, in particular for unsteady data sets. Today, we're still mostly shared memory, although, again, as Scott pointed out, one of the key things that we're evaluating is how to get it off of this as quickly as possible. It looks like there's a question around.
We do, by the way, pretty much all of these heavy-duty calculations use multiple grids. So we are utilizing the cores available on the CPU.
There were some questions about looking at structural data. For those people who are interested in more of the structural analysis and perhaps a little less on the fluid side, we haven't really talked about that. However, we do have those capabilities as well, and perhaps we'll add that to our to-do list and perhaps put on a little more of a seminar around how one can analyze results from structural studies. Looks like there's a question around shock locators.
Where's
what about transient shock locators?
Oh, well, that's a good question. I think you're thinking in terms of a shock feature extraction and transient flow. I don't have a good answer to that.
And Andrew, we'll follow up.
We'll follow up with you,
and we'll try to send that out to the audience. We didn't talk about the time average capabilities, but perhaps it's worth just showing you quickly since it's pretty easy to do. We do have the capability at this point to integrate over time, and we're still working on making this a little easier, so there's still some work to be done there. But if we just look at a scalar integral of, say, vorticity magnitude, and we can actually select a series of, say, just the isosynthesis. Each one is at a given time step, so there are about 50 of those or so. And if I just go ahead and integrate those, we can actually integrate across. So we're looking at integrating across each one of these, and we'll actually get a list. I forgot to plot the results, but you can plot the results as well. So here represents then the average of those values, integrated values on the isosynthesis vorticity. Okay, a while ago I had a problem with loading 255 files, totaling about 8 gigabytes. TechPlot loaded those files, and even though the required machine had a lot of memory, did not save the layout and so the whole data. I'd be curious to know, whether or not you're looking at the most current version of TechPlot. We have made some significant improvements.
Yeah, over the last 2 years, I guess, we've improved the performance of TechPlot by an order of, well, a factor of 3 or so, and so it really depends, and identified some of these bottlenecks. So, TechPlot 360, yeah, they were all called 360, so it would be, I would say, get the latest version. If you don't have it, if you do have it, you can contact us offline, and we'll help you with that.
For those people who are interested, we will post the slide deck, so you're more than welcome to keep a copy of that as well. Okay, let's see.
Oh, is there another option, exporting movies and loading frames in AVI? Yes, we actually have, the new version will have an MP4 export. And there's a couple of other options we've had around for a while.
Yeah, we added MPEG-4. That's certainly one that's come up quite a bit. Can you generate visualization for 3D glasses? Not yet.
Not yet.
But I suspect that's coming. Yeah. Longcham's not here to say it all.
I'm sure he's listening, though.
Okay.
I'm using software on Mac here. Plot 3D loader. Yeah. I'm assuming that question related to the Plot 3D loader and time accurate solution is related to moving grids. And yes, the new version of TechPlot can handle moving grids or changing grids, in with Plot 3D files.
Okay, we have time for maybe 2 more questions. So if you want to go ahead and ask now, we'll still have a couple on here.
Comment on the time average capability. Did you mention that? Yeah.
Well, I just did the integration. Yeah. I did a simple scaler, but if we wanted to, we also can do the averaged as well.
Typically, there you end up with a data set that represents time as one of the variables, and then you can do the averaging over time.
And of course, if we do that integration, one of the things that we're implementing, and I don't think it's in the build that I have right now, is the ability to plot that as a function of time. So that's forthcoming. Should be there soon. Okay. Will you have a native open foam loader? Good question. We're working on some strategies around that. But can't comment on when that'll be available.
I don't know any more than you on that. But yes, we are working the problem. Let's just leave it there.
Well, I am curious. Hey, are you going to have a statistics calculator, min, max? We do already have statistics in TechPlot. I don't know if I have it loaded. In fact, I didn't load it, but we do have statistics capabilities built into TechPlot.
Yeah, we have a simple. It's actually an add-on, and you can load it. Go to the manual. It'll tell you how to do that. But it's stat. I think it's stat. Stat.dll if you're on a Windows machine.
We have time for one more question. Give you a second to type. I think we hit most of these, although non-uniform mesh. We missed any early on. Okay, the low volume. I think we're good. Okay, last question. We have someone who's asking about laminar turbulent transition on MAV wings. I think it's just a type of work.
Oh, yeah. Well, that's very interesting. That's pretty exciting, actually. I'd like to see that.
Okay, good idea to include them on, okay, when we switch on and off the strand ID.
So we have a strand editor where you can go in and change those. I'm not sure if that's what your question was exactly, but
yeah, so
it looks like that's what your question is.
Yeah, there is. We built in that capability a while ago, so you have the opportunity to, in fact, edit the time strand, which, depending on the plot, you can actually edit time strands, and you can build in additional time strands. Will we fix the audio? Sure do hope we can.
Yes. That's a top priority.
Yeah. Could you show me the input data options? Okay, the last thing we'll show here is just quickly, these are the data types that we can load, and they range from the typical structural codes to common CSV types. Okay, well, again, wanted to thank everyone. I'm sure if you have additional questions, feel free to go ahead and email us, and we'll make it a point of getting back to you. Can we superpose time accurate plots, CPU issues? That actually might not be difficult either. I think that's fun by looking at it. I have a couple of examples I don't want to load right now, but you can actually look at a time accurate CD plot.
Right, and you can superimpose it, yeah, I think we can do what you're asking, but
yeah, and so yeah, in effect, if you're interested in a little more detail on that, perhaps we can take that offline and try to get a little more detailed answer. Well, again, thank you everyone for spending some time with us this morning. Really appreciate your attendance. Profile for multiple things, sounds available. We'll take that one offline. Again, thank you, and we have the next session coming up will be a lot more tactical. Please, if you have some things that you'd like to make sure that are covered, feel free to email us and let us know the things that you'd like to see, and we'll make sure that we cover that on our next webinar. Yes, thank you, everyone. I'm sorry about the audio problems. We'll certainly try to figure that out before the next one. Yes.